First of all, thank you for coming to hear us talk. Thank you for the organizers for organizing the event. And also thank you guys, that was an amazing talk. I think we can all agree on that. I'm Anna. My background is in mathematics. I did a degree, master's and PhD in mathematics, and after that, I've been working in the AI space for almost 10 years. I have lots of different jobs. I had very hands-on roles. I've been a data scientist, I've been an AI engineer, but I've always been a tech lead, and I had other leadership roles. I've been really involved with startups. I've also founded a couple of startups myself, the first one in 2017, then another one in 2021, and my last one last year. That is in tools, for which I'm the CTO. And today I'm gonna talk about what AI actually is. And I have 3 goals for today. One is that you guys have a lot of fun. It's not a technical talk whatsoever. So hopefully it's very digestible, and we end up the talk really understanding what AI actually is. And also hopefully you'll leave this room today understanding that AI is actually a technology problem and not necessarily a people problem, like we see and that we hear a lot on social media. And this doesn't continue well. Technical question. It doesn't work. It's not going. It's all right. We can use this. Right. So we hear a lot in lots of events and in social media that AI is actually not a technology problem and it's a people problem, which I totally disagree. So hopefully this gives you a little bit of insight of the technology side of AI. So the first thing that I want to do with you guys is actually what AI actually is for you. So if you can use your phones, you can actually scan this QR code, and what I want you to do is to write down what you think AI is. And if I have set up that properly, your answers should appear there.
Can we go back one slide?
Yes, of course, absolutely no problem. Right, let's see what keeps on popping in there. Yeah, well, artificial intelligence, yes. True. Hand the road, okay. Presumably the angel, okay. Cognitive suppressor, a very useful tool, right, interesting one, is statistics, right. Transformation of fuzzy data, a family of techniques for finding answers to problems, okay. Very diverse questions, well, answers, sorry, I would say. All right, we have, science fiction, right, overhyped assistive technology, right. So, gonna go back to the slides, thank you for that. Shall we play the game? Yeah, good. The game is called AI or no AI, and it's a very quick game. I'm going to show you some images, and I want you to tell me if what I'm showing you is AI or is not AI. Are you ready? Yeah. Go. Okay, let's go. AI or no AI? Right. AI or no AI? AI or no AI? AI or no AI?
Can't see it.
Controversial. AI or no AI? Okay. AI or no AI? No AI? Okay. Right. AI or no AI? Okay. AI or no AI? Right. AI or no AI? Are you sure? Well, this is actually my cat. I mean, any excuse is good to show you how cute Willow is. But look, we're gonna have a look at what AI actually is. And some of you guys mentioned in the Slido that AI is a tool. And actually, well, yes, ChatGPT, Claude, and Copilot can be part of what AI is, but it's not all what AI is, and Lewis has demonstrated that today. Today, convolutional neural networks are actually another type of AI. I would say a particular algorithm that falls in a subtype of AI. So AI is not a tool. AI is actually a field. So the same with the mathematics, physics, and chemistry are fields, AI is also a field. And it's a field that studies systems that behave in a way that resembles intelligence. So that doesn't mean that they have intelligence themselves or cognitive capabilities, but it's like something that looks like it does have intelligence. And like any field, it is a combination of methods, techniques, algorithms that have also subtypes. So, we're going to talk now about the types of AI. And what I'm going to do is like a nested classification on how that can look like. And you would think, okay, why is this something important to know? And it's because not every single type of AI is suitable for every single problem. So it's important to map each type of AI to different type of problems that exist, so we actually find the right solution for our problem. And definitely, LLMs are not solutions for absolutely every single problem. So the first one is the whole field. So anything that gets a system to behave like it's intelligent. Within AI, we have machine learning, that Lewis has mentioned this today, and it's the part of AI where algorithms learn from data. There are 4 types of machine learning. We have supervised, unsupervised, semi-supervised, and reinforcement machine learning. And I'm not going to get into the technical details of this, but depending on the type of data and the type of task that you're trying to solve, you will have a different type of machine learning. So for supervised, we have data sets that are labeled, right? So you would have a data set, for example, that gives you the characteristics of houses, and you also have the price, and where you're trying to predict, so the task is predicting the price. For unsupervised, what we're trying to look into your data is patterns and groups. Semi-supervised is a mix of supervised and unsupervised, and reinforcement learning is a paradigm in where agents are getting data from the environment and taking actions. We hear this a lot. Your model is not as good as the data you feed it, and I don't agree with this, because you can have the best data in the world, but if you don't choose the right model for your problem, then the solution that you're going to have is not going to be very good. Within machine learning, we have deep learning, which is a subfield of machine learning that uses algorithms with a particular type of architecture called neural networks that we've seen today. And within deep learning, we have this particular type of algorithms that generate new content, and that is a field of generative AI that we hear a lot now. And within generative AI, we have LLMs. So those are particular models that fall into the category of generative AI that have a particular architecture that is called transformers. So as you can see, large language models are actually a very small part of what AI actually is, and there are lots of other different types of AI and lots of other different types of algorithms that exist, each one for a particular problem, and not every single one is solving every single problem in the world. So what about agentic AI? Because we hear a lot about AI agents, so I want to ask you guys a question. Where do you think it sits? Any other ideas?
Is it engineering rather than science? It uses the LLMs underneath it?
Aha. So, actually, agentic AI, I think, is more like a paradigm more than anything else. So it actually sits in any type of AI. So it can be just LLM-based, or just like classical machine learning-based, or a combination of them. And it's basically this paradigm that is used to chase a goal by planning, making decisions, and executing tasks with minimal or non-human intervention. So it seems that we have forgotten about this. And this was actually very big at the time. I'm not totally sure if you remember AlphaGo, AlphaZero, then, well, AlphaFold had a combination of lots of different things. The latest versions had LLMs. But I put here a couple of examples that at the time were very famous, but there are lots of different types of AI agents that are actually not LLM-based. Well, reinforcement learning uses actually the terms of agents a lot, and reinforcement learning has been there for decades. I'll share with you the slides, so if you're interested to look at the videos, those videos explain really well what these are. But basically are agentic solutions that don't use LLMs in the background. The last one is quite cute. I will recommend it. Right, so I show you guys a nested classification, but in every single ring, there is stuff that doesn't correspond on the nested category below. So there are things that are artificial intelligence that are not machine learning. There are things that are machine learning that are not deep learning. There are things that are deep learning that are not generative AI. And there are things that are generative AI that are not LLMs. So for AI that isn't machine learning, that is any algorithm or any technique or any methodology that doesn't use data. So for example, rule-based systems, that is considered as AI, but is not machine learning because it doesn't use data to learn. And actually, like traditional chatbots, that's how they worked, really. They were rule-based systems. So for example, it was like a customer chatbot. If the customer inputted like the word order and then the number of the order, we'll be able to pick that, then check in a database and just, you know, have a predefined structure of how that text was going to look like and just output that with the status of the order. Then we have machine learning that isn't deep learning. And those are all of these algorithms that their architecture is not a neural network. I was showing you in this AI game, I was showing this equation of a line. That is a regression line. That is a machine learning algorithm. And that doesn't use a neural network as an architecture. It's just a straight line. Not used a lot for obvious reasons, too simple, but definitely a pedagogical example. Then, yes, deep learning that isn't generative AI. So when, I don't know who was asking the question about the hallucinations to this. So convolutional neural networks are not generative because they are not generating new content. And there are lots of algorithms actually that fall into this category of deep learning that is not generative AI. So for example, I don't know, recurrent neural networks, LSTMs and others that are just predicting an outcome and not generating new content. And then we have generative AI that is not LLMs. And again, I feel that we have forgotten about the first big phase that were generative adversarial neural networks, and then a little bit further down the line, variational autoencoders. So those are algorithms that are deep learning algorithms that are generating new content that are not LLMs. Right. So I want to get a little bit deeper into the difference between classical machine learning and deep learning. And that is, classical machine learning is the part of machine learning that is not deep learning. So those models that don't have an architecture that follows the neural network structure. So with classical machine learning, you need to choose your own features. So it's really good that you've given this talk because it's helping me a lot to reference lots of things. But for neural networks, we were seeing before that the neural network itself was choosing the features, right, and determining what was important. But for classical machine learning, you need to do that work. You actually need to do that work manually. So that is called feature extraction and feature engineering. So feature extraction is determining what are the features of your data. If you think of an Excel spreadsheet, the columns of your Excel spreadsheet. But what are the features that are important and are going to create the best output when you run your machine learning model? And if those features don't exist in your data set, what are the configurations that you're going to do in the features? So you can do, for example, like a combination of features, like a linear combination of your features, and create a new features to put that into your machine learning algorithm in order to do your predictions. Another difference between classical machine learning and deep learning is that in general, classical machine learning needs much less data than deep learning. And you would think, and we do this a lot in You're okay? Sorry. Sorry? So I see this a lot on social media as well, that the more data the better, and the bigger the model the better, and that is just not true. And also from a computational perspective, if you could have a model that is achieving the same results, but it's consuming less data, and it's consuming less compute, for me, is a no-brainer. Right. What a neural network actually is, I'm not going to get into much detail on this slide because we covered that in the previous talk. But basically, neural networks are an architecture of deep learning algorithms that are based actually in the neurons on our brain. The reason what they're called, that what this part of AI is called deep learning, is because the more layers that you have in your neural network, the deeper it gets. So basically you have your input, you have your output in your neural network, and then you have as many hidden layers as you want. So the more layers, the more complex it gets. Right, we're going to talk now about how machine learning actually works, and I'm going to bring my very innocent and naive example of the equation of a line. And I promise you that this is the only equation of this talk. So, in the world of language models, we hear a lot the concept of parameters, right? So this model has 7 billion parameters, whatever, right? But what does that actually mean? So, let's start with the equation of the line. So we have y equals mx plus c. M is your gradient, so how inclined your line is. And c is your y-intercept, so where the line crosses the y-axis. Right, m and c are weights that need to be adjusted. So let me explain that. You have a data set, right? Let's go back to the example of the houses and the pricing, right? So imagine that we're trying to, this is very simple, right? But bear with me. Imagine that we're trying to predict the price of a house based on the number of rooms of the house, right? So what we would have is a data set that we start with. So from data that we have collected, I don't know, from our neighborhood, right? That tells you the price of a house depending on the number of rooms. Or let's say square meters of the house, right? I think is a better example, right? So we have that historical data, right? And what we do is we place this equation on the line randomly in the middle of our data points. That means that m and c have a value, but it's a random value that we're going to start with. Okay, so that is this first picture there. So at that state, our model is not fitted, so nothing has happened. We have just placed it there. Right. So what we're going to do, first iteration, we're going to move our line a little bit, right? And what we're going to do is we're going to compute the error, which is the distance of the line to each of the points. We're going to sum it, we're going to do an average. That is a value that gives us the error. Great. So for that particular line that we've moved, we might have changed M and C. Okay. Then second iteration, we move our line a little bit more. We compute the error again, and then we compute the two errors. Right. Is the error more or less than before? If it's more, it's not that way. We need to come back. If the error is less, we're going in the right direction. So we keep on moving, and so on and so forth and so forth. So after some iteration, we will get a plateau in where we're just not minimizing the error anymore. So that is our trained model. So for that particular line, we have a particular value of M, a particular value of C. So those are adjusted weights, and those are our parameters of our model. So obviously, this is a very simple example. So with that line, that would mean that for any square meter that we put in the value X, we will get our price, right? Because that would be Y. And we'll be able to predict more data points. Right, this is really simple, right? It's just the equation of the line. But the models get more and more and more and more complex, especially the more parameters that you have. And this is in 2 dimensions. There can be 3, 4, 5 thousands of dimensions. You can't think of that, if you can, let me know. And I have put there a couple of examples. So the first one, yes, the equation of the line. The next one is a particular type of neural networks with 25.6 million parameters. The next one is one of the latest open source large language models with 753 billion parameters. So you can see that the range is quite big. And the more parameters, the heavier is to store, but also to run. So I want to clarify two important concepts when it comes to talk about machine learning. One is training and another one is inference. Because I also hear a lot of this. Oh, we've trained our own large language model. No, you haven't, right? That has not happened. What you've done is probably either fine-tune it or do some inference. So training is basically going through the process that I have just explained to you of fitting the data into your model and finding the parameters that best predict something, right? So that is done once, right? And when you have your model trained, then you can use it to predict stuff. And when you're predicting things is when you're doing inference. So for example, when you're using ChatGPT, Claude, Copilot, whatever, and I put the example of this more contemporary AI tools, there's no training happening whatsoever at that moment. What these companies do with your data, that is another talk. But what is happening is that you're just doing inference. So those models are already trained for you, and you're using it to predict tokens that we'll get there in a second. Okay, we're going to talk about deterministic versus probabilistic. I think this is a topic that is a little bit confusing as well, and I hear lots of misconceptions around this as well. I read on social media a lot that AI is non-deterministic, or like LLMs are non-deterministic, whatever. Okay, let's have a look at what this actually means. So, a model that is deterministic means that after you train the model, when you give it an input, you're always going to get the same output. Okay? Non-deterministic or probabilistic means that it's based on a probabilistic distribution. We're not going to explain what that means, but that is simply that when you give it an input, the output will be different every single time that you give it the same input, no matter how much you're changing the parameters of the model. There are lots of algorithms actually that are non-deterministic, that are not LLMs, right? Because I think there is this misconception that anything that is not an LLM is deterministic, and this is not true. Because there are a lot of algorithms that are probabilistic by nature, like the deep learning algorithms, machine learning algorithms, so there are more. LLMs are non-deterministic, even if you put the temperature equal to 0. Okay, so the temperature is a parameter in your large language model. What you have, what you just have to P, you have to K, that determine how creative your large language model is. So that means is that the more chance of getting something different in your output with the same input are you going to have. And you might think, well, why would I want that? Well, if you're developing an app, Rick and Morty, have you watched that episode? Oh my god, this just came to my mind. Okay, sorry, back to the talk. If you're developing an app that is about creating stories for kids, you want that to be creative. If you want to develop a customer bot support, for example, for a university, you want to give your students similar, right, customer support. So you might want that to be as deterministic as possible. The problem is that with LLMs, you cannot switch that off. And this is because they're not reproducible, because that depends on the hardware they're running. So you might get, for example, let's give an example of predicting if an image is a cat or a dog, which, by the way, you wouldn't really use an LLM for this, but just so we understand. So you get a cat with a score 0.7 here, right? And then you get, in the second run, just checking the time, a score of 0.69999. So in that case, dog wins instead. So the rest of the sentence is built on that and not on cat, and that can happen in different runs, even if your parameters are set to 0. let's talk about LLMs properly, and let's understand what's going on behind the scenes of these AI tools. So an LLM is a next token predictor, and a token is not the same as a word. So it can be a word, but it can be part of a word, and we also count spaces and punctuations and all that stuff. There's no one universal tokenizer, so that is a model that basically converts sentences into tokens. There are lots of different ones. I put an example there, that is the one that GPT-5 and 013 use. Actually, if you type OpenAI tokenizer, you can actually check it yourself. And actually, that can be another machine learning model or not. It can actually be just a script. If you just decide to chunk your words in a particular way, you don't need a machine learning algorithm to do that. All right, so when you create your tokens, it turns out that LLMs do not understand words, funnily enough, even though they're called large language models. What they understand is vectors, so they understand numbers. So what happens to those words is that those words are converted in something that we call vector embeddings, and those are vector representations of the word. So let's think of a two-dimensional space again. So words that are semantically similar would be placed in a space, in a vector space, closer, right? So in this case, for example, the words cherry and pear, because they are fruits, they are closer together in the vector space, but they are very far away from tablet. And as you can see, apple in there is between the food groups and the tablet, because it can be a fruit, but it can be a brand, a technology brand, right? That's a non-contextualized embedding. So that would be for an embedded that actually doesn't take into account the meaning of the sentence, right? But they are embedding models that actually take that into consideration. So I was talking about embedding models. So those are models that actually create these vector representations of the words. The model has no memory between calls. This is another misconception that I hear a lot, and is that the models actually can remember things. They actually cannot. That is something that is enabled in the tools, right? So you're using, I don't know, if you're using OpenAI, you're using the GPT family of models, and then ChatGPT has memory enabled, so is remembering all the conversation. So basically what's happening is that all the memory is being passed in the context window, which is something that is finite. Something that these tools do actually is compact the context window. There are lots of different techniques to do this, but basically because it's finite and it's not forever, what they do is these summaries of what you have already been talking to the AI tool, so it can remember kind of the conversation. Right, so to wrap up, I cannot believe that I'm finishing on time. When LLM is not the right solution, so those are actual real cases I encountered, that a more simple solution of classical machine learning, or even not even AI, because AI is not a magic wand that solves all the problems in the world. So those are cases that I have actually encountered. That certain startups, companies, people that I work with were using LLMs for, when a more simple solution was a better solution in terms of simplicity, compute, cost, even transparency. So for example, for like software development, automations and scripting, I've seen lots of people using LLMs for this, when just a simple script works, like classical automations of the development that we have been doing for years and years and years. Sentiment and text classification. So I've been seeing people basically determining if tickets of clients were negative, positive, or neutral using Claude. What a waste of tokens when you can use classical NLP for that. demands and sound forecasting, RMA models were absolutely fine for these things, but there are also packages in Python that have been developed specifically for this that are deterministic, that work perfectly fine. From there is current as well. So, well, if any of you guys have been in the data science space for the last decades, I think like 8 years ago, everyone was using XGBoost for absolutely every single thing, and it worked absolutely fine. And then, yes, for parsing fixed format data, regex parsers and validation rules work absolutely fine. Not AI whatsoever. And that's all, folks. That is me. Hope you enjoyed the talk. Hope you have lots of fun and that you understood what AI actually is. Thank you so much.